Okay, functions. Now, I don't know what your book or how your book defines functions. We're going to do it this way. We are going to say a function is a rule. That's key right there. It's a rule which relates to objects. The input and the output. That's going to be our definition in this class of a function. Now, just as an aside, definitions in mathematics are usually like, especially when you go on in math and you start taking like more abstract math classes, you'll get a definition of something and you read it and you go, what? You didn't tell me anything. Like this right here doesn't tell me anything about what a function is. But that's kind of by design. You see, the less that we specify, right? In other words, the more general or the more broad we are in our definition, it ends up being more powerful. We'll see an example of this in just a second. But usually, and like I'm guessing in your textbook, instead of saying relates to objects or something like that, it'll say relates to sets. And in particular, they probably say sets of numbers. And yes, in our class, pretty much every function that we deal with will be kinds that take numbers as inputs and give numbers as outputs. But the thing about it is, if we keep it more general, if we keep our definition more broad, it actually turns out to be more powerful. And then everything that we learn and discover about functions, all the theorems and truths that we're going to find out about functions, will be able to be applied in a much wider, in much wider situations, right? And if we go ahead and say, oh, it's a set or it deals with numbers, then we're missing out on a lot of the power of what we have. So it's kind of why definitions in math sound like nothing, like what did you just tell me, but so that's where we're going to start here. And I want to give an example to kind of give you an idea of, and we'll, like I said, we will be working with functions whose inputs and outputs are numbers, but I don't want to start there because I want you to just have in your mind, like it doesn't need to have anything to do with numbers. So, okay, got this. I'm going to erase it. Good. All right. Uh-oh. Okay, so I guarantee that you have come up with this function on your own before. Let's say that you want to write a message or a code or a letter to your friend or something like that, but you want to do it in a secret code, right? Like you're pretending you're spies or something like that, and you want to write a letter to your friend. And so you come up with this idea, you know what? Instead of writing the letter A, I'm going to be clever here. And instead of writing A, I'm going to write a number. And then you're like, that number is going to be 1, right? And then you think, well, hey, why stop there? Instead of writing B, I'm going to say, instead of writing a B, I'm going to write the number 2. Now, instead of writing the letter C what do you think? What number would I write instead of C?
3.
Right, yeah, 3. Okay, okay. And so on and so forth. And I guess D would be 4, E would be 5, and so on. And then we finally get down to Z, which would be, what number would Z be?
26, 8.
Yep, I think so. Last time I checked, there were, I didn't actually count it, but the last time I checked, there were 26, right? So, okay. So there's this relationship. In fact, there's a rule, right? That we haven't explicitly stated what this rule is, but there is a rule that relates these two objects together. And right now, these objects happen to be sets. The set on the left are just the letters, right? They're the letters A, B, and so on all the way down to Z. And this set is just the natural numbers from 1, 2, and all the way up to 26. So this right here, the input set, is what we call the domain. So our domain. That's our domain. Now, I'm going to give a definition of what the output set is. It's called the range. So I'm going to go ahead and call it the range. This set of numbers is the range. And this, like I said, this happens to be a set of numbers, but you realize this didn't have, the first set didn't have anything to do with numbers. And the second set didn't have to. I could have chosen emojis if I wanted, right? I could say, instead of writing the letter A to my friend, I'm going to write a smiley face. And then a B will be a frowny face. Or I could have mapped them to colors, right? A is red, B is green. It could even been a mixed set. I could have said like A goes to green, B goes to happy. And so now I have this mix of colors and feelings. As long as there's a rule. Now, here's something I didn't specify, and it should go in our definition, is that every one input maps to one and only one output, right? Like, it wouldn't be much good if, well, we'll get to that in just a second. Let me talk about what the range is. The range. These are the values you get when you plug in, and we're going to be doing this so many times today that by the time we're at the end of our hour, you're gonna, like, any ambiguity in this, you're gonna totally understand. You'll get what we're talking about. The values you get when you plug in the domain. Okay, so that's the range. Values you get when you plug in the domain. And I mean like the entire domain, not just one or two of them. The range isn't just what you get when you plug in, say, A and B. It's when you take the entire, all of the input values that you've defined, every single output that you get, that entire collection is called the range. So again, the values you get, the output values you get when you plug in the whole domain. Okay. All right. So now I'm going to erase this definition here. Am I good? Erase. All right. Okay. So now. So there is a rule. We haven't stated what this rule is. There's not like a formula for it or anything, but we could see like, yeah, there's a rule and you know exactly what it is. When D is the input, you know that the number what is the output?
4.
Right? Yeah. See, I haven't written what this is. Actually, I'm gonna call this inputs. And these guys are outputs. I didn't write out an explicit rule, but you know that there's a rule. And in fact, I mean, this is kind of explicit, right? I mean, I could go through and write the remaining 20 whatever letters, and then we would have an exact rule for everything, but I'm being lazy because I don't feel like writing all that. You probably wouldn't see it if I wrote it that small anyway. So there's a certain notation we use for a function. And what I'm going to do right now is define this function as f. F for function, right? And so there's this function f. And we define f to be the function that takes letters A through Z as inputs and gives you numbers 1 through 26 as outputs in this way, where A goes to 1, B goes to 2, all the way down to Z goes to 26. And the notation that we use for functions, this is what trips more students up than anything else, is this. So we have the name of the function. In our case, we're calling it f. And then we do this type of thing. We have f and then parentheses. And what f does, in fact, I want to do this in a different color. We're going to say f is black. This spot right here is where the input goes. We take any of our defined inputs and we could put it in there. And once we do that, right, once we actually throw in an input, so let's say, let's make it easy. Let's start with the first one. How about A? When I plug in A, then this entire symbol right here, everything that I've just written right here, is a shorthand way of writing the output itself, which in our case is A goes to the value 1. So if you were to see this, if you were to just see on a piece of paper f of, and it's called f of A, we say the name of the function and then of some input value to mean f evaluated at A, which is the actual output value. That is, now this is the key, is that this entire symbol right here represents the output. So if I did something like this, if I said, okay, f of something plus 5, like if I wrote, say, f of b plus 5, b, that's right. If I said f of b plus 5, I would know, well, hold up. This entire thing, that just represents the output that I get when I plug in a b. So I look over here and say, okay, when b is the input, 2 is the output. So that entire symbol right there represents the number 2. Like this is kind of what goes through my head when I see something like that. It's like, oh, that whole thing represents the number 2. And I just say, oh, that's just 2 plus 5 in this case. Okay, 2 plus 5. So that is equal to 7, I think. Yeah, last time I checked, 2 plus 5 is 7. So, okay. Now, another thing we could see, another way, can I erase this right here?
Yes.
All right. So just kind of really driving the point home, if I said something like this, f of, how about, let's go C, f of C. And I had, I don't know, maybe a 2 in front of it. Something like that. I know, buddy. So if I had 2 f of C, what would go on in my head is like, well, wait a second. F of C represents an output. And so I'm kind of thinking about it like this. I see, okay, there's the f of C. So that entire symbol right there is just a fancy way of writing some output value, which is a number. And so I think, okay, again, I'm just kind of drawing out what goes on in my head. Like, okay, that f of C is a fancy way of saying the output, which is 3. And now we're thinking about this when I'm just going to use this, right? That whenever you see 2 numbers next to each other, that means multiply, right? I'm sure you've seen that before. Like if you see 2x, that means 2 times x. I'm not writing the number 23 here, right? I'm saying 2 f of C is the same thing as 2 times f of C. And so 2 times 3 in this case would be 6. Okay, so that's just some, that's the idea. And this is, I'd say this is the most difficult part about this stuff. Well, one of the most difficult parts is that seeing that this symbol right here, F with some input value in it, represents an output. That it means the exact same thing as this. So when I write F of C, it means the exact same thing as 3. Okay, now, can I erase this stuff?
1 second.
Okay.
Yes.
Okay, now, so let's think about our secret code. Now, let's say I wanted to write you a message. And what I want to say is, hi, Kayla. But I'm lazy and I'm not going to write out K-A, I'm just going to say hi, K, because I'm lazy. And that's one thing we're going to talk about a lot in this class is how lazy mathematicians are. And almost everything we do is to save ourselves from doing more work. Like we try to get by with a minimal amount of work in math. And so I'm just going to go ahead and use that. Okay, so if we wanted to write this to our friend, right? So I want to send you this secret message. Well, I don't really need to in fact, if you were doing this, you wouldn't think too hard about it. You would just say, well, H, let's see, A, B, C, D, E, F, can't see, F, G, H. Okay, H is the 8th letter. That is, if I would have written all of this out, we would have known that H gets mapped to the number 8. HI is the next one. So I guess, would be the number 9. Let's see. J would be 10. K would be 11. Okay, so K is 11. Okay, there we go. And again, if I weren't lazy, I would have just written out the entire alphabet, but I'm lazy, so I didn't, right? So anyway, this is already in our heads. We have the definition of the function. It has all this information. And now I could say, okay, if I wanted to write this to you, I would say, well, H is represented by the number 8. And so I could just say, oh, okay, I would write you 8. And then I is 9, so then I would write a 9. And note there are spaces here. This isn't 89, right? Like we understand, like as you're writing this to your friend, you're gonna space it out so that they understand what you're doing. You're not just gonna like write 705 and like, what is that, right? So we go 8 and then we go 9 and then K. K is 11. Okay. Now, what did I just do? Let's think about what I just did. Okay. Yeah, K. So what did I do? In order to find 8, right, I basically said, well, what does my function tell me that the letter H goes to? And this is all I did. I said, well, I plug in an H, I get out an 8. Okay. And then in the second case, I said, okay, I plug in an I and I get out a 9. I. Then I plug in a K and I get out an 11. That's what I did in my brain, right? I took the input, did whatever, I followed whatever rule there was. There's some kind of rule for computation. And I said, okay, when H goes in, 8 comes out. When I goes in, 9 comes out. When K goes in, 11 goes out. Cool. So then I send you this message, right? And you receive this message, 8, 9, 11. Now, in fact, I'm going to go ahead. We're going to take it up a notch. We're not going to cheat. We're going to say, all right, now, what just happened? You get your message in the mail, you open it up, and it says 8, 9, 11. And you go, oh man, what did Justin say to me? Well, what are we going to have to do? We're going to have to think about our code, right? But there's something going on here. Like, you know that I'm not trying to tell you 8, 9, 11. You know that what I've done is I've evaluated this function. That is, I took some input, did something to it, and got a different output, right? And so you say, well, when Justin wrote an 8, what he actually meant, you see, what he did was he took some letter, plugged it in, and got out an 8. What was that? Well, then you look at your code, right? You look at your rule, you look at the definition of the function, and you say, well, when 8 is an output, H was the input, right? So you think, well, that must have come from the letter H. Ditto with 9. You say, well, I know that he plugged in a letter and I got out a number. The number is 9 is the output. So then I must have been the input. And you go, okay. Oh, he's saying hi. Okay, now you say, okay, now the letter is the output is 11. So he plugged in a letter, got out a number. The number he got out was 11. That's what he wrote. So he initially.
Okay, left. 5.
Okay. Now, what did you just do? Well, we have symbols for this, actually. What we've just done is it's called the inverse of the function. Have you heard this before?
No.
Good. Okay. We're doing new stuff. Excellent. So this is called the inverse of the function. It's like, so a function is a rule usually for computation or something like that. And it, of course, relates inputs and outputs. The inverse is kind of the opposite. We know, like I was just saying, when you get this message, you know that I have written a code to you. You know that this came from somewhere. There was some input value that gave you this as an output. And so you went and said, well, what was that? What was that input value? Well, we know the code. 8, the input must have been H. 9, well, the input must have been I. That's called the inverse. And we have a nifty little symbol for that. So, in fact, I'm going to do this in black because the numbers are black, and F, remember how I said F of something represents an output? Well, the inverse is going in the opposite direction. It's like saying, well, if we have an output and we want to find the original input, we're actually going in this direction. We're taking outputs, and think about this. It's like outputs are my new inputs, right? So like when you have this, you're like, well, how do I get back? You take that output value and you say, well, I need to do something to it to give me another number. We're just undoing what we basically just did. And so we call this the inverse. We could give it another name, like, I don't know what comes after F, maybe G. We could call it G. We could say this is a new function, G, and it has the property that it basically tells me what the input was. Given any output, it tells me what the input was. We could write it. The thing is, we normally don't give it that name. We give it a special name or a special symbol when we do this. And we write it like this. This is going to look weird. F inverse. It's F with a little -1 up there. Now, that doesn't mean that we're actually like raising F to the power of -1 or something like that. Like a lot of people think that that's what you're doing when they see this symbol. It's like, oh, wait, so we take F and then raise it to the power of -1, so we like divide by F. It's like, no, not exactly, because, well, check this out. We're not dividing anything. We're not, this has really nothing to do with math. Like I said, I could have mapped the letters to emojis, or I could have mapped them to colors. This has nothing to do with math. This is just, or this has, rather, this has nothing to do with numbers. And so it's not like -1 means raise it to the -1 power. It's just, it means that when you see this symbol here, F to the -1, it means that there was an original function, F. There was an original rule which related these inputs to these outputs. And now we're playing the game where it's like, well, I got a bunch of outputs. I have the secret code that you just gave me, and I want to decode that. It's like you've encrypted a message, and I need to decrypt the message. I need to go back to where we started. That's what F inverse does, the inverse of a function. So the way we would write that, so like we did before when I had my original message, hi, Kayla, and I think in my head, okay, well, H goes into F and out pops an 8. I goes into F and out pops a 9. We could play that same kind of game and say, well, if 8 was the output, then what was the input? And so we say there's this function, F inverse, which is another function, right? In this case, it's another function. It's something that relates inputs and outputs, relates two objects together. There's a set here that it takes as inputs. And we say, okay. And this is just like kind of in symbols what our brain has already done, right? Like we knew the code. We knew, like you knew that when you got the message from me, 8, 9, 11, that you're like, oh, wait a minute, 8 actually came from a letter. And so you plug in your head, you plugged in the number 8 and said, where did it come from? Right?
8.
And so we plugged in 8 and said, ah. That gave me an H. In other words, this symbol, the inverse, F inverse of 8, represents or is the same thing as the number H. The number H, the letter H. When you were like, wait, 9, what did he say? You said, well, 9 was an output to a function. So the input must have been, and this is what, in symbols, this is what your brain did. You said, okay, there was a function. Now I need to go in the reverse direction. 9 was the output. And so you say, well, okay, then where did that come from? And that's what your brain did right here. And it turned it into that letter right there. You said, oh yeah, if 9 was the output, then the input must have been I. And so then you know that's what I put into the original function. That was my message to you, right? Finally, you said, okay, Justin wrote me a message. He wrote an 11. What he did was he put a letter into a function and out popped the number 11. So you say, okay, what was that function? Well, here's my relationship. When 11 is the output, then K must have been the input. You just did another function. You said, okay. Right there, everything I just said was this. You said, we need to undo, right? We're undoing the original function. And so when the output was 11, and you did that, and you went back and said, it must have come from the letter K, like that. K. So, okay. Any questions thus far?
No questions.
Okay. This is the relationship. This is basically, this is a symbolic mathematical way we could describe a relationship, right? We're relating to, I don't even want to call them quantities. I'm calling them objects. Because quantity makes you think some kind of number of something. Again, this didn't need to have anything to do with numbers. It's just kind of, it's an easy example to do when it is. Now, let's think about this. So first off, I want to test your understanding. I didn't ask if that was good to be erased. We're done? Is that okay?
It's all good, yeah.
Okay, cool. Okay, I'm going to put a few things up on the board and I want to see if you're tracking thus far. So let's do this. Let's go F. We'll do a couple of these. Okay. So if I said, what is F of Y? What is F of Y?
25.
25, yes. Okay, you're tracking. What about, let's do F of E.
5.
5, yes. And right now you're like, okay, yeah, I get it, but I really want to beat this point home. Okay, now this is where it's gonna, here we go. What's F inverse of 4?
D.
D, exactly. So what did you do in your head? You did it, right? You're like, well, hold on. You're telling me that 4 was an output with this strange relationship, right? Or you're saying, I got a secret code somebody wrote me, and the output was 4. The input must have come from the letter D. Now, okay, one more. Let's do this one. Okay, F inverse of 23.
W.
Oh, is it? Hold up, yeah. 26, 25, 20. Yes! I was like, no, it's X. Yeah, no, you're right. That's W. Okay, yes, W. That's fine. I thought, what's 1 less than 25? Well, 23. Okay, anyway. Now, what about this? What is F inverse of, let's say, F inverse of 32?
That doesn't work. There is no 32.
It doesn't work, right? Yeah, exactly. It's like, wait a second. You're telling me that you used this rule, you plugged in one of these 26 letters and out popped a 32. No, it didn't. That never happened, right? So this there, and so technically if I say this equals what, well, first off, this makes no sense, right? We could say this isn't defined. We don't have, actually we wouldn't say it's defined. We would just say this is nonsense. This is like, you plugged one of those letters into F and out popped a 32. No, you didn't. No, you didn't. That it's impossible. It doesn't make any sense. Why is that? Well, it's because 32 is not in the range, right? This only makes sense to take the inverse of something. It only makes sense if you're talking about actual outputs that are indeed in the range, right? Just by the way we define range, right? I said that the range are the outputs you get when you plug in the domain. This is not one of those outputs. It's not in the range. So we could say then the only allowable values that can go into the inverse are actual outputs from the domain. Otherwise, none of this makes any sense, right? Okay, so similarly, we could do this. We could say, what is, if I were to ask you, what is F of beta? That's a, oh, that looks too much like a B. I don't want to do that. If I wanted to say, what is F of alpha? I love that I could like use Greek with you. I don't have to like, usually it's not until you're in college and stuff, and then you have to be, okay, now this is the letter alpha. It's a Greek letter. Anyway, so what is F of alpha? And you'd say, yeah, I don't, whatever you want it to be, right? Like, it's now this, we would, in this case, you're trying to plug in a letter that is not in the domain. Well, this is not defined. This is not defined. Now, what I could do is, let's say we've been writing each other letters for a while, and I say, well, yeah, we might want to like speak some Greek to each other, right? I mean, especially if I want to say like Kyrie eleison or something, then maybe I could then extend this function. And then I could say, okay, you know what? We're going to extend the domain here. I'm going to say maybe alpha is 27, beta is 28, and so on and so forth. But as it stands right now, this is not defined. I'm going to run into this a lot. Like you may have heard before that you cannot divide by 0. Do you know why you can't divide by 0? It's not defined. You could, and actually, in some cases, you can define it in certain cases, and it does make sense, and everything stays nice and consistent. But for the most part, and especially in our class, division by 0 is not defined. We haven't, so this is, yeah, this is basically the idea of a function, is that it's, and I think about it as, well, first I think about it as a relationship. We have two things that are somehow related in some way. We have inputs and outputs. And there is a rule which tells us how to relate these things together. Now, one thing I did not say, and this is important, this is probably the most important thing about this, and I didn't even include it in our definition because at first it wouldn't really make sense, as though the original definition made sense to begin with. But okay, I'm going to go ahead and erase this stuff. But this is so important. This is so important. I'm going to write it in red. So we said a function is a rule which relates, which gives, we're going to say for every input. Write that out in English. For every input, one and only one output. When you see this definition, like with most definitions in math, you're like, okay, great, what's the big deal? Well, let's think about why we might want this. Let's suppose that this function that I just defined, f, we're calling it f, it's our secret code, f. Let's say that I went and said, okay, b gives you both 2 and, I don't know, 71 as an output. Okay, so it gives you 2 outputs. All right, that's cool. But then how do we go about, so if I had then a secret message, right? And actually, let's do it this way. Actually, this would be a little bit better. Let's say it gives me 2 and 5. And I say that the output of A is 1 and 3. And then I wrote to you some secret code, and you got it. And the code was this: 1, 2, 4, 3. You'd say, oh, okay, Justin just wrote me a secret code. And he said, well, 1 must have come from A. Okay, so that's A. 2 must have come from B. Okay, there's B. 4 must have been D. Yeah, okay, so he said A, B, D. And 3 must have come from, uh-oh. Was that an A or a C? Huh. Not sure about that. And so now there are things that give that when you get one input, it gives you multiple outputs, but they are not functions. We don't call them functions. So, and again, something that had this property wouldn't be very useful, right? Be like, well, it's kind of ambiguous, right? So this is what we mean by this, that every one input gives you only one output. It's just one of those things we have to have. Now it's going to get tricky. If it wasn't tricky enough, I know we only got a couple minutes left, but as if it wasn't tricky enough, I'm going to go and make it really tricky. Now, so I give you this relationship and say, all right, this is how we're defining f. And you look at it and you say, and if I were to ask you, is this a function? You'd say, well, yeah, there's a domain, there's a range. Every one input gives you one and only one output. But now let's say that I went and did something like this. Now, in the same, it's kind of the same situation here. It's like, and now if I were to write you the secret code, and I write 1, 3, 5, you're going to say, okay, 1 came from A. I'll come back to that. 5 must have come from E. 3, again, we're kind of running into this ambiguity. It's like, I'm not sure what you meant there. Did it come from B? Or did that come from C? What was he trying to say to me? What was the original thing? This is a case where, now this is the thing. Now I'm going to ask you, is f a function? And well, by definition, yeah, it is. You have a domain, you have a range. And for any one input, you get one and only one output. By definition, this is a function. No question about it. I'm not trying to be tricky. It is a function. But the inverse is not a function. Why? Well, for any one input, for that one input, I get one and only one output. For that input, I get one and only one output. But for the input 3, the input, now we're thinking about, these are my new inputs, my range for the inverse function are the new inputs, it's the new domain, and we're saying, well, what about 3? Well, 3 gives you both B and it gives you C. So then in this case, the inverse is not a function. And we will see examples when we start doing it with action. We're not like talking about letters and numbers and kinds of crazy stuff like this. This will make much more sense. And when we're talking about functions of real variables, which is what we're going to be doing for the rest of the time in class, we're going to have functions which take real numbers as inputs and give you real numbers as outputs. Then there is a much easier, or this makes a lot more sense in that context. And there are easy rules for determining if something is a function, if its inverse is a function, but we'll be talking about that. For right now, I wanted to just introduce this idea, and I did not want, because I really don't want us to get our blinders on and think, okay, functions are something you do with numbers. That's not the case. Functions are much more general. It is simply just a relationship between two quantities, and not even quantities, a relationship between two objects. And those objects don't even need to be sets, that'll blow your mind. But like, what's not a set? Isn't everything a set? Yeah, no. So my point is, we're going to be dealing with mostly sets of real numbers, and that's what quiz 0 is all about, really, is just kind of getting used to dealing with sets, how we write sets of real numbers, how we could describe different sets of real numbers. And so, yeah, so this, if you feel a little lost, don't worry, this is supposed to be real high level abstract stuff. But I love this example because it makes perfect sense, right? And especially when I say, what's F inverse of 32? And you go, that doesn't make any sense. Exactly. If we do this, if we start off with numbers and I did a similar type of thing, be like, well, I don't know, but I'm sure we could find out. It's like, no, it doesn't exist, right? Like, it's easy to see with this kind of example. So I wanted to start with this example. We are out of time. Do you have any questions?
I do not. This made a lot of sense, actually. kind of made sense. So
that's excellent. Excellent. Good. Okay.